happy to have Davide Gaiotto from the Perimeter Institute, who will speak about categorical Hooft expansion. And please keep in mind that it's rather mathematical audience, so
Absolutely.
yeah, all right.
I wouldn't speak to anybody else.
All right, so go ahead. Thank
Okay,
you.
very good. So I would like to discuss some aspects of sort of holography, string theory, and the relation to gauge theory, which I believe are sort of ripe for mathematical formalization, and I think should be sort of interesting to develop further. So the sort of general collection of questions arises when you think about the possible ways to define string theory. So at the moment, we roughly have two different ways to define string theories with very small overlap. One goes back to the very origin of the relation between string theory and gauge theory. You start with the gauge theory of large matrices with some UN gauge groups, say, you take n to be large. And there is something called Hooft expansion, which I'll describe momentarily, and which supposedly produces string theories. On the other hand, when you study string theory course, I don't know, you read Polchinski, you start from a completely different starting point. You want to describe strings that move in space-time. So the trajectory of a string is the two-dimensional surface in space-time. And so you define a theory that lives on the surface and tells you how the surface moves in space-time. This theory is technically a topological field theory in a cohomological sense. I will call that the dg-TFT. Think about each algebras, each two-factorization algebras, these sort of things. And starting from this two-dimensional topological field theory, there is a procedure called the genus expansion, which also supposed to produce a string theory. And sometimes these two definitions overlap. These are the best understood examples of holography. In holography, I take something like chemical force super Mills, which is a UN gauge theory with a lot of fields. And this is supposed to be, in the Hooft expansion, is supposed to give me strings moving in some dimensional space-time. But we can also write down the worksheet theory that describes the motion of strings in this dimensional space-time. This is what makes the duality interesting in a sense.
So may I ask you a stupid question? So
yes.
You say UN, and so n will go to infinity as far as I understand. But
yes.
there are other gauge groups for which non-classical.
Sure. You can do quivers. You can do
but
other
if
classical
there
groups.
is but if it's non-classical, if it's just a group G, whatever compact, what is it a rank which should go to infinity?
No, it has to be specific. It has to be a classical group.
Okay. So n is important for you.
Technically, you want to be able to work in the link category. So you can take the link category of UN or other ones.
Yeah. Okay. Good. All right.
Right. So, I mean, for example, the standard UN gauge theory, the one that describes the strong interactions, say, supposedly, I mean, by this Hooft expansion should correspond to a string theory, but we have no independent way to describe the string theory, no worksheet description. And so we cannot in practice do anything useful with that statement at the moment. Ideally, we would like to have just one path to string theory. So my ultimate goal is to say, give me an algorithm that takes a UN gauge theory and produces a worksheet theory. With genus expansion, we reproduce the Hooft expansion. And ideally, this procedure will be sort of completely transparent and rigorous, a mathematical construction. So let's see if we can put a bit more details on the board to make sense of this statement. Formal deformation theory helps a lot in formulating mathematically rigorous statements in this context. First of all, in a sense, holography, this Hooft expansion works not just for individual gauge theories, but for families of gauge theories. So the first thing you could say, let me just take a gauge theory and start deforming it, study the formal deformation space of this gauge theory. And then I'll apply the Hooft expansion and get a formal deformation space of this closed string theory, which is basically the quantum master equation for the closed string theory, the quantum version of equations of motion, if you want. If you take a classical limit, then you can get the classical equations of motion, so the string theory. And on the other side, on the lower side of the board, the genus expansion relates formal deformations of the worksheet TFT to the classical equations of motion that closed string theory. So we got a bit, immediately a bit closer to closing a circle. It says we can go from the gauge theory to the master equations, to the classical limit, to the deformations of the worksheet. Now, if the deformations of the worksheet told us everything about the worksheet theory, it would be done. Unfortunately, that's not quite clear. But there is something
sorry, kind of, you
Yes.
see, I told you that it's a mathematical audience,
Yeah.
so I am sure that people are already lost. So you have something which you called UN gauge theory, whatever it is. Okay, without specific, for example, Chern-Simons theory is okay.
I mean, open Costello-Guillen.
I don't know. I haven't read Costello-Williams, so I'm not at the perimeter.
Pick any of the many perfectly mathematically formalized. Everything is perturbative here, so I want to stress. I was going to stress in the next slide. So
no, but the first question, UN Chern-Simons.
Yeah, Chern-Simons is great.
Okay, great. So now you consider kind of a moduli space of deformations of your gauge theory. So there are some parameters which...
That's a homology problem.
For example, you have, I don't know, the action functional, and you add with some coefficients, some terms
Absolutely.
to it. And these are sort of local coordinates on the moduli space. It can be described some formally as a solution to some quantum master equation.
Absolutely. That's slide 5.
Okay. Now, at the very low...
I wanted to give an overview before I get into the details.
No. But I would like to have some kind of translation, very vague. So when you say, let me skip this DG and just think about TFT, because, okay, so good. Then you can ask the same question, deforming this TFT, yeah? So which depends on some parameters, something like deforming associative algebra.
Absolutely.
Yeah, and it's described by sort of a Maurer-Cartan equation, which is classical master. A quantum is a sort of a quantum version of this Maurer-Cartan. And there is some parameter which goes to 0 in the classical limit. What is it?
Yes. Well, we can call it h bar.
H bar, okay. Some parameter called h bar. Okay, good.
I will Yes.
Okay, thank you. Yeah.
Now, the Maurer-Cartan equations for the worksheet TFT give us a lot of information about it, right? The H2 algebra structure is already there pretty much. But if you really want to present the GTFT, a two-dimensional topological field theory to a mathematician, well, they will invoke Lurie and they will say, okay, give me a category. Give me the, category of boundary conditions and object there.
Yeah, but sometimes, for example, if you do have whatever Calabi-Yau category in mathematical sense, then you can construct, I understand, 2D vault sheet.
Exactly.
So in some cases, mathematically, yes, it's understood. Yeah.
That's right. So when you say Calabi-Yau category, what you mean is literally the formal deformations of a 2D theory with 1D boundaries. So you deform the theory and the boundaries. The deformation space of boundaries is the Calabi-Yau category. So if I understand formal deformations of 2D theories with boundaries, then I'm done.
Yeah, but I believe here that mathematically the lower part of your diagram is understood, but the upper part is...
Well, I get there, but
yeah, all right.
So now, I need boundaries for this worksheet. So I need a setup where the equations of motions of string theory will tell me about the formations of the boundaries. This is called open-closed string theory. So there are some objects called D-branes, which correspond to boundary conditions on the worksheet. And when you put the D-branes in the game, now you have open strings whose endpoints are essentially attached to the D-branes. And you have an open-closed string theory whose equations of motions are the deformation theory of the 2D worksheet plus 1D boundaries. And there is also a quantum string. So you can do this at quantum level. So there is a quantum open-closed string theory. And in the Hooft expansion, you can ask me, how do I put these D-branes in the quantum field theory? And there is an explicit answer. So you take your UNGH theory, you add some extra degrees of freedom I'll describe momentarily, and you study the formal deformations of that. So I'm predicting that you can build a category just from the gauge theory, a category of modifications, and this category will be defining a worksheet theory.
But these modifications, are they what? Certain deformations? Or?
No, they are modifications rather than deformations. You add degrees of freedom, and then you deform.
So your modified gauge theory will no longer be gauge theory or what?
It will still be a gauge theory, but originally it was a gauge theory of matrices.
Okay.
And now you add vectors.
Well, you add more parameters. It's like, imagine you
can...
Sure.
Once, just give me a slide.
Yeah.
So but when you add these vectors, you get new parameters, which are the open strings. And so, now that you obtain hopefully a worksheet theory, you can do the genus expansion. You can ask, is the result the quantum master equation? Is the result the Hooft expansion of the original theory? So, and let's see, as I said, most of this is mathematically almost done, right? As I said, you open Costello-Guillen, and you can get a definition of your gauge theory and its formal deformations. And you just need to apply to the correct theory and organize it in the correct way. And you should be getting...
but just since for those who have not read Costello-Guillen, so in what language I should think about the top line in your diagram? Like gauge theory is what?
So the top line is pretty much a definition. So on the left-hand side, you have some calculations, perturbative calculations in gauge theory, Feynman diagrams and stuff like that, in BV formalism, ideally.
But initially, it's what? It's factorization category, it's, I don't know, vertex algebra.
The theory will give you factorization algebra. Absolutely, which encodes the Morey-Cartan equations for the theory. So you take your modified theory that gives you a modified factorization algebra. And we somewhat organize.
All right. So maybe you later will explain. Yes. I'm not sure. For in the only example which I understand.
I'll do matrix models.
Then I know two examples. Yeah, matrix models and Chern-Simons. It's two.
Yeah, maybe I should answer Simons as an example. Maybe I'll do that
later. Maybe not today. Okay. Thank you.
Very good. So the top left is mathematically rigorous. The Hooft expansion is just a combinatorial game. It's not a deep thing. So going from the top left to top right should be straightforward. I'm not saying it has been done already, but I can see that the relevant theorems could be proven in a short amount of time. The classical limit is also pretty straightforward. So the first mathematical theorem would be so that the outcome on the bottom right it satisfies the axioms of the coborgism hypothesis. One will have to sort of prove this theorem, which I think will be mostly automatic, but will require more work. Then the genus expansion is also mathematically already on reasonable grounds. Kosiewicz and Costello again have told us how to build the genus expansion out of a dg-TFT. So now there is this becomes a conjecture which can be proven. The genus expansion of the theory, or the worksheet theory, reproduces the Hooft expansion. So it's a collection of theorems, right?
Yeah. Hold on. Yeah, I mean, it's too many things. Yeah, I believe that everything for you is rigorous, but maybe not.
No. I'm saying that I can see this becoming a theorem with a few years of work.
Yeah, but what I would like to understand is what kind of a theorem do you expect? So again, you said that the top left rectangle is mathematically understood, but for that I have to read Costello-Williams
Yes.
many hundred pages. All right. Okay, but assume that it's understood. The bottom left, I understand that in some examples, like again for Calabi-Yau categories, it's our work with Maxim, and also I believe Costello wrote also something like 20 years ago. We did it. Yeah, and then it's very well the left bottom left rectangle is understood, so I can speak about deformation theory and adding whatever I want. So the lower part is clear. Now, what kind of a theorem that for any UN gauge theory plus some modifications, whatever I
It's
don't
not
know,
plus some modifications, that's like plus
modified.
all modifications. So they form a category.
For all. All right. But anyway, for this left upper rectangle, what? There exists something in the bottom left or what?
Yes.
And you,
No,
okay.
not just, it's not that, so you take this, you apply a completely mechanical procedure to go right, bottom, left, so that you apply
it's a definition of the right, bottom, left. So your purpose is to construct this dg-TFT or what?
Right, so I'm saying that just by turning a crank, one should be able to go from the gauge theory to this worksheet theory. And then the theorem would be that the genus expansion of the worksheet theory recovers the Hooft expansion of the gauge theory.
Yeah, but you do not have the vertical arrow from gauge theories to dg-TFT. So that's
you do, because I put two equal signs, and then there is a vertical arrow on the right.
Yeah, but then this means that you define it. So there is a way, but it's a I do not understand because it's a definition, and probably by your definition, the genus expansion coincides with the Hooft expansion because there is no alternative.
No, be careful. So the classical limit loses information. So at this quantum master equation, I take the classical limit. The classical limit gives me a worksheet theory. Now, I would like to prove that from the worksheet theory, you can go back to the quantum.
Invert the vertical arrow if on the right. You have from okay, good, thank you.
That's right. So there's this classical limit that loses information. But if the genus expansion works, it should recover the information.
All right. So very informally, you have something classical on the bottom, and you want to quantize it going up.
Yes, that's
something like that. Okay.
That's right. And if you ideally, I think this, in an ideal world, this would be done for whole classes of gauge theories at once. But for any specific gauge theory, if you can prove this theorem, you'll have proven holography for that gauge theory pretty much. So holography is a pretty important topic in physics and in quantum gravity. So having rigorous proofs of it, I think would be cool, even in toy models. And also in the process, I hope that you can do interesting mathematics. Like, you produce some interesting categories or some, in a sense, in here, there are like huge generalizations of conservation formality theorem, of also the quantization theorems. There is many interesting mathematical topics that can be put inside this, can be organized this way.
Yeah, I would really be glad to understand the analogy with formality theory, but maybe later when you
Yes,
explain more. Yeah.
that's right. Any other questions before I move to the slides? No, just I'll now repeat everything, but it's a little bit more detailed. So first, I want to describe what's the UN gauge theory. So it's a quantum field theory, meaning there are some fields, at least in perturbation theory. These fields are valued in adjoints of UN. So they're just big, n by n matrices. And you give an action for this theory. This is a single trace action that is classical, meaning if you want the action to contain traces of products of fields and their derivatives. So you can write the most general action this way. I put the one average bar in front as a loop counting parameter. There are couplings, G alpha, and there are all possible, cyclic invariant words made out of fields and derivatives. Now, typically, your original gauge theory will be defined by a handful of terms. But in perturbation theory, you can imagine turning on all the couplings to study the formal deformation space of the theory. So these G alpha, a few of the G alphas can get a final value if you want, the kinetic term or something like that. But most will be treated as formal parameters.
So, for example, if I have a quiver with potential,
Yeah.
it will give me a theory. Yeah.
Absolutely. There will be the matrix model that I'll be describing later on.
Okay.
And this G alpha will be sort of associated to the essentially the cyclic homology of your category. Okay.
Okay, we'll see.
Now, this is classical. When you define perturbation theory with a renormalization, there are counter terms. In principle, in matrix require counter terms which have multiple traces multiplied together. This will be suppressed by powers of H bar, and they're hopefully not going to change the structure of the Hooft expansion that I'm going to describe in the next slide. Although I think, mathematically, it would be nice to have theorems or work analogous to Kosterlov-Williams that, just tell you, oh yes, you can certainly renormalize the theory in a manner compatible with this larger expansion.
But in the end, you get a formal expansion in what? In H bar, in the powers of H bar.
Yeah, so for any quantum field theory, you would have a power series in H bar, right? There'll be some fun, whatever you're computing, I don't know, the free energy, a scattering amplitude, or a connected correlation function, you always get, a three-level part, which goes like one over H bar, a one loop part, and that goes like one, and then higher loops with higher powers of H bar. For UN gauge theory, this will be functions of the couplings and of n. But because the Feynman diagrams only involve, contracting indices, working with fundamental representations, you can do it all in the link category. N enters polynomial initial this.
Yeah, but in the link category, you have only one continuous parameter, and here you have what? H bar or product or lambda or your lambda? What?
Well, initially I have H bar, G, and N. Then there is the Hooft expansion, means that I'm just reorganizing a little bit, writing in terms of H bar and NH bar.
Okay.
It's nothing super deep. Just the combinatorics of Feynman diagrams tell you that if you do this reorganization, the powers of H bar will also reorganize in a convenient way. So after you reorganize, there will be something that goes like 1 over H bar squared times a function of the couplings and of this Hooft coupling and H bar. Something goes like 1, something goes like H bar squared, and so on and so forth. This is the Hooft expansion.
Only even powers of H.
Only even powers, that's right. And there is a general expectation, which has been proven, I think, in a handful of examples like matrix models, that the power series in lambda actually converges. in NH bar actually converges.
Sorry, does it mean that each term converges, or if you
Yeah.
combine all the terms?
No, for each term. So F0 converges, F1
Okay.
converges, F2 converges.
Okay.
Now, I will not use this fact. It's certainly nice, but I'm perfectly happy to work formally in lambda. That doesn't make a difference for the argument I will give.
Okay.
But right. So if you want to do really holography with gravity in some manifold, then you need to be working with this resummed in lambda. Okay, so this is the Hooft expansion, and it starts on the gauge theory and it produces this thing, which we can formally call a string theory.
Sorry, before you go, okay, if I have just this two expansion, whatever it's defined, kind of with all details filled, so can I produce a two-dimensional whatever TFT, which gives me the same expansion, or what?
So at this point, I will try to describe how to derive the deformation space of a 2D TFT. And then I will add the fundamental modifications to get
without modifications, one cannot say how to produce, how to match. Okay.
That's why, so when I say categorical Hooft expansion, I sort of mean Hooft expansion with modifications.
Okay.
So now, if you think about string theory from the point of view of the worksheet, as I was saying, I should give you a two-dimensional topological field theory, or even better, a deformation family of these two-dimensional theories. Let me call them T of T. Sorry for the name. Then, this one thing you can do mathematically or physically with the topological field theory is to evaluate it on a Riemann surface. Sorry, on a surface, not Riemann surface, on a surface with some genus. The evaluation in the conventional topological field theory, the evaluation gives you a number, but in a dg-TFT, when you have each algebras and things like that, you can get instead a form on the space of surfaces.
When you write T of T, T of G and lambda, is it the same or it's different?
So the parameters T will take the same role of G and NH bar. I'm sorry, I should not have used G for the couplings. I apologize. Here G was the couplings of the theory. Here G is the genus. I'm sorry.
Yeah.
That's the only time I will. Sorry. Okay. In this slide, G is used for different things. I apologize if I can.
Yeah. But when you write T of G lambda, G is a genus.
Yeah. Okay. So let me just replace this G with
maybe
N.
No, this, yeah, perfectly okay when MG, if MG is a modular space of curves or whatever.
Yes.
No, it's fine for me with this G, but
okay.
your goal,
yeah.
G.
So the point is that you have this, if you're the correct Calabi-Yau condition, right? The topological field theory can be evaluated on a surface to give you a form. The space of surfaces is contractible to the space of complex structures on the surface. So you can try to integrate this form on the space of complex structures. And if you had the correct Calabi-Yau condition, like 2D Calabi-Yau, then you can integrate it in principle on the modular space of Riemann surfaces. This quantity is the answer of what defines the string theory. And it depends on the choice of topological field theory. So it's a function of these parameters T.
That's fine, but what I see that there is H bar in the story, there is G, which is genus, there is genus in the story, but there is no N in the story. Yeah. N is absent.
Absolutely, there is no N. That's right. So
what do you mean match?
Match means find the topological field theory such that the parameters T can be identified with the couplings and the Hooft coupling.
Okay. Lambda is one of the parameters.
Yeah, that's right. So one of the parameters should be spatial and should be an H bar,
okay.
and the other should match the gauge theory
I
coupling.
see. Okay.
And this is supposed to give me f n of T. So I will declare victory if I can find the topological field theory such that, sorry, now it's not letting me. What's happening? Okay. Oh, no, sorry. How do I write the annotations? That was silly, apparently. Sorry. Okay. Sorry. Okay, so right, so I declare victory if I can take the Hooft expansion and find the topological field theory which reproduces all the terms in the Hooft expansion as integrals on the moduli space of Riemann surfaces of a partition function. Okay, so technically it's useful to work in the BV formalism on both sides. So in gauge theory, in the BV formalism, you have the space of couplings becomes a dg space, and you have a quantum master equation that describes this formal deformation theory. On the side of the dg-TFT, well, the dg in the name just already meant that everything was derived, and you know the deformation theory of the dg-TFT is contained in the sphere partition function. Like the derivatives of the sphere partition function give you the operations of the issue algebra, for example. The sphere partition function is an action for the issue algebra.
May I try to kind of to repeat or to ask? So your spaces will be spaces maybe formal graded whatever manifolds.
Yes, like
formal pointed graded manifolds with endowed with odd vector field. Which corresponds to the differential.
Sometimes there will be BV infinity structure. So it will be
yeah. But I am talking now about classical structure. And classically, so you have something like super manifold with a vector field of degree 1 and a symplectic structure, odd symplectic structure. Yeah. Such that probably your action will satisfy the classical master equation, which its bracket with itself is equal to 0.
Yes.
Okay, this is classical story. And so that's correspond to this bottom of your slide, yeah?
Yes.
Without quantization. And you want to somehow to quantize it.
That's right. So, that's right. So the genus expansion somehow gives you a quantization of the formal deformation theory of this Julie theory.
Okay.
And hopefully it will match the Hooft expansion of the formal deformation theory of the gauge theory. Okay, so now it's time to talk about, again, I'll give an example of matrix models between this lecture and the next one, so hopefully it will help a bit. For now, I want to sort of define still on an abstract level fundamental modifications. So for fundamental modifications, you have your theory of matrices, and we're going to add some fundamentals. So literally things that transform in the fundamental representation of UN. So after you do that, you need a new action. You need to add something to the action for these new fields. And what you add are mesons, meaning that there are things that look like an anti-fundamental, a sequence of matrices, and a fundamental. I denote here as U bar W alpha U. Because you have multiple copies of these fields, this U bar WU is itself a K by K matrix. And so the couplings will also be K by K matrices. So these new couplings S alpha are K by K matrices. And again, you have to normalize this, and you have to be careful in doing so. But this defines a new system with a formal deformation theory, which now includes both the old couplings and these S's. Perhaps I should have added a slide here, and I didn't. So there are many ways you can add fundamentals. Like, I don't know, if I have a theory that lives in 3 dimensions, I could add fundamentals that live in 3 dimensions. I could also add fundamentals that live on a 2-dimensional plane only, or along the line, or perhaps even just at the point. So there are many ways to add fundamentals to the theory. And you can add many of them at the same time. If you add 2 types of fundamentals, you could build mixed mesons, right? Mesons which have one leg on one fundamental.
So it's already scary. You see, meson, I heard this word studying physics in school. But if I have a quiver with a potential, right?
Yes.
And just take just one coupling constant, so one parameter deformation. Yeah. I don't know. Adding what you call fundamentals at the level of the potential means what?
It means adding a framing. For example,
adding framing to the quiver.
Yes, for example, consider the ADHM quiver for simplicity.
No, this I do not
Consider
understand.
ADHM.
What depends what do you call frame?
I have
when you say
UN,
framing, you allow arrows in both directions.
Yes,
yeah?
yes. So I have a UN node. I have, maybe some loops.
Yeah.
Which represents, matrix fields. And then I can also add
yeah.
Vectors.
Yes, some framing vector spaces, but arrows can go in both directions. So if you have a matrix which is represented
X, Y, and Z. I don't know.
So then adding fundamentals can be thought of as considering a new potential on the framed quiver.
That's right. I could take something like that, right? The old X, Y, Z. Trace of X, Y, Z.
Yes.
Plus.
I see. That's familiar story. Yeah. You modify the cyclically invariant word by adding something new. So because you have new arrows in the framed quiver, you can multiply your whatever.
Absolutely.
Yeah. Okay, good.
So now I get new couplings, which are matrices, K by K matrices. And, as I said, suppose that I had 2 different ways to modify the system. Then I could have used, what the fundamental for one and the anti-fundamental from the other. So every pair of modifications, I get a space of couplings. That's you start seeing sort of a category, right? The modifications are like objects, and the couplings are morphisms.
Yeah. May I ask you another stupid question? I understand that S alpha, they are not numbers, they are matrices or whatever.
Yes.
Yeah, but let's just pretend that they are diagonal matrix, like scalar matrix. So I take S alpha out of the trace. So these are just
then there is no trace. Yes.
No. What I'm trying to say, or maybe it's even not essential, that you have a kind of space like toy model. You have a quiver with a potential. You can do 2 things. You can upgrade or whatever, replace quiver, but it's framed version, and you can deform the potential. What I mean that should I think of this as alpha as a deformation parameter or sort of coordinates on the space of deformations of the potential?
Yes,
Or
yes,
it's too
absolutely.
naive? Yeah.
That's right. That's right. Yeah.
Okay.
Yes. Notice also that these alphas in that example of the quiver will also be living naturally in the Ginsburg algebra.
Yes, yes. What I mean that originally you have Ginsburg algebra, which gives you sort of resolution, which is quasi-isomorphic, whatever, to the Jacobi algebra of the path of this quiver with potential. But now, if you deform the potential, your Ginsburg algebra also get deformed, so everything differential gets deformed.
I would prefer to think about it in a slightly different way. So the original if you have a matrix model, an equivalent potential, I would associate to it your algebra.
What do you call
The one was Kosul dual is the Ginsburg algebra.
Kosul dual to Ginsburg algebra?
I would say the Ginsburg algebra is the Kosul dual of yours, but yes, anyway, you Kosul dualize twice and it's the same.
Okay.
So the W alphas are literally elements of the Ginsburg algebra. That's all I was trying to say. Right, because they are sequences of words. They're words, sorry, they're sequences. And so, in the BV formalism, you can really see the Ginsburg algebra out of the BV bracket and of these words, of these mesons. Anyway, maybe I will get there. We'll get there. Sorry.
Yeah, all right. Go ahead.
Yes. Okay, so now that I've introduced these modifications, I can do the tooth expansion again. The structure is a little different. Now I have two organization parameters. I'm sorry, the G again, you're supposed to be an N. Too many G's. So
why do you don't like G? G is a genus, is it correct or not?
Well, yeah, I didn't want to cut to. I'm using G for the couplings, so I'm not happy to use G for the
no. I'm not religious. Well, I rather keep
You're
G
happy with
as a
having
genus
G with
because
multiple meanings. That's fine. Like example, call the couplings tau or something. Anyway,
yeah.
So now the point is that the S's are matrices. They always appear as sort of a trace of products of these S matrices. So B counts the number of traces of products of S's. G is the genus. And so now you have this double expansion in G and B of certain functions of the parameters, the matrix parameters, and the tooth coupling. And as I was saying, this in a string theory perspective, what I've done is I've added D-branes and open strings. And the S's are the open strings, the G are the closed strings. Roughly. And yeah, it's all same before. You can modify the theory in multiple ways, and so you get a category of modifications because the couplings of mesons are, have one leg on one modification and one leg on the other. Okay. So now let's compare this with what we know about two-dimensional theories with one-dimensional boundaries. So the one thing we know is that if you take, I should draw a disk here, but so if you have a topological field theory with boundaries, with it, which is sufficiently good with unframed, sufficiently framed, not unframed. Then you have the boundaries form a three-dimensional Calabi-Yau category, an infinity category, and there is an action for this category, and this action is the disk correlation function, the disk partition function, the evaluation, the theory evaluated on a disk. And it should be compared with sort of the F01 in the previous board. Because if you deform,
I'm really confused with the first phrase. It's F01 of S, which from your previous slide. So in fact, it's S. There were kind of G is equal to 0. Okay, this I understand. One means indeed sort of one component. But where is three Calabi-Yau structure comes from?
Now you tell me that mathematically you use the 3D Calabi-Yau to define what topological field theory is, and that's perfectly fine.
Yeah.
Physically, the way a physicist would discover there is a 3D Calabi-Yau category is by looking at the disk, the partition function on a disk, for the boundary condition deformed by S. So
and then you expand, and
you expand in powers of S. S is a matrix,
yes.
So it's a non-commutative expansion.
Yes, and
these are the structure constants of your category.
What are the structure constants?
I mean, if you have let's say algebra instead of category. If you have a three Calabi-Yau algebra,
okay.
You have an action.
Yeah.
If you have a category, then you can start doing more interesting disks, right? Where you use boundary 1, and then
I think I understand what you mean mathematically. It's naively speaking again, that if you start with an algebra and do some kind of this, whatever, Maxim and myself or Costello, this kind of construct a theory out of the Hochschild complex. So you need to have, to get a three Calabi-Yau, you need to have a scalar product on this algebra, and probably that's what you say when you put whatever.
Yeah, the scalar product, in particular, the disk 2-point function.
Yes, it's
on the undeformed boundary.
okay. And so, but when you think the other way around, when you start with an expansion, you say that the scalar product is defined by this boundary condition. All right.
Yes, that's right. And of course, you can deform the bulk too. And so if you expand this out, you get both the infinity algebra, but also the action of the HU algebra on the A infinity algebra. So anyway, the cobordism hypothesis tells us that this data sort of fully captures the topological field theory.
So let me, so what captures, so you say that some data completely allows us to completely reconstruct.
Yeah, F01.
F01, okay.
Yeah.
F01, but kind of as a function on the space of parameters on the moduli space, which means that like I can imagine that I can differentiate it with respect to S.
Yeah, S is a formal parameter, so it automatically already a power series.
Yeah, all right. Okay.
So now you see where I'm going. If I do the Hooft expansion, I get my F01 of S, forget G. S is what matters. Of S. And that's hopefully dg-TFT.
But this, I forgot this cobordism hypothesis, that it's a kind of theoretical statement. that if you want to write down explicitly what are these infinity compositions and Calabi-Yau structure, can you, or maybe you can, yes, expanding in the parameter S,
Yes.
yeah, probably.
And typically, you don't
Okay.
need to give me the whole category, right? Where often you give me an object and then modulus for that object is enough or something like that.
Yeah, okay, all right.
Okay. So of course now the question will be, can you prove a theorem that the F01 produced by the Hooft expansion is always giving me a 3D, a 3D Calabi-Yau category? So I do my story in the quantum field theory. I compute F01, and then is this defining a topological field theory? And then topological field theories appear here often non-compact. The cobordism hypothesis might need to be adjusted a little bit. I don't know. I hope it's not too much of a complication.
Maybe, I don't know. Yeah, but for me, the most complication is to understand mathematically, since I have not read this Kevin's book, what this Hooft expansion mathematically. Yeah, yeah,
Yes,
okay.
I understand. Okay, so let me see, how much time do I have?
You still have time, so go ahead. Yeah.
Okay, so I wanted to start talking about the matrix model example a little bit, and hopefully finish it in the next lecture. So for simplicity, let me look at the quiver with one node and arrows. So I'm going to look at this a UN matrix model. With a bunch of adjoint fields. And okay. So, formally you just take an action, which is a linear combination of words. You exponentiate the action, and you integrate in a middle dimensional contour in the space of complex matrices, such that the integral converges, divide by the volume of UN, and then defines your partition function. And then the thing we're calling F will be sort of the logarithm of this in a perturbative expansion. Which contour we pick doesn't matter. In perturbation theory, you always automatically use the steepest descent contour. In practice, when people try to solve the matrix models or study matrix models, what they do is to study what are called loop equations. Loop equations are integration by part identities. I've just estimated if I integrate a total derivative, I get 0. If you work in a BV formalism, then you will want to add antifields, maybe add a ghost and an anti-ghost, and write a more general BV action that contains fields and antifields. And then in the BV formalism, these loop equations become essentially the quantum master equation. So, there is a BV differential, which is sort of divergence. It eats up. It's a second order differential operator that eats a field and an antifield. And this sort of the consistent actions, the space of formal deformations of your matrix model is actions which satisfy the quantum master equation. Now, to get a derived, to really get a derived description of this formal deformation space is actually better to not impose this quantum master equation as an equation, but just say that this is exact if you want. So what you can do is you can find a differential operator that acts on the couplings, such that differential operator plus BV Laplacian equal to 0. This differential operator has the useful property that it will annihilate the partition function of the matrix model, and essentially gives you a derived version of the loop equations. I mean,
what do you mean find? Do you mean that it's an additional question? Find
no,
this
it's automatic. It's automatic, meaning you active delta BV on e to the action. Delta BV will produce, will pull down some traces, and then you rewrite the traces as derivative of the action.
Yeah. But the coefficients of this, the first, okay, hold on.
Yeah, you're asking why the H bars?
Yeah, for example, this one, yeah, why?
So this is sort of, okay, I don't know how to answer the question. It says that, so this H bar counting, I learned it from string theory. For me, it's just, when I say, well, string theory, that's the H bars I'm gonna put. But in practice, if you just do this calculation, you will find that this H bar, this way of distributing H bars is convenient. Like every time you pull down a trace, by doing a derivative with respect to the couplings, it's convenient to put an H bar squared. And then you have a 1 over H bar squared in front of everything. Yeah. So, I mean, what I'm saying, with this definition, H bar only enters the way it's written. So with this definition, there is an H bar square in front of the derivative with respect to the coupling, and there is a 1 over H bar square in front, and that's it. So what is this Q? Concretely, Q has roughly 3 terms. There is a term that sort of is the classical master equation. It takes two, takes 2 copies of the action and brackets them. This is the sort of tau bracket tau term. Then there is some linear stuff. There is in particular, it doesn't matter. There is a term that is proportional to NH bar. There is a differential, which is a constant term, and they're proportional to NH bar. This is the only place where n enters. This d of NH bar. And then there is a co-bracket sort of thing, which comes from the fact that when you have you have a trace, the trace is a bunch of fields and antifields. The delta, the BV operator eats a field and an antifield. So what leaves behind sometimes is the product of two traces. And so this gives you this sort of term in Q, which is a second order differential operator. So just by looking at this B algebra structure, the action of BV on traces, you automatically gain a very rich structure. You can find a DG-lead B algebra structure on the cyclic homology of Kontsevich-Stolbermann algebra.
Yeah, why bialgebra?
Because there is a bracket and a co-bracket. The bracket takes two traces and contracts two fields to make a new trace. The co-bracket takes one trace and it breaks it by the action of delta BV. So it contracts two fields that are far from each other using the pairing.
So you have the cyclic complex where everything happens and where you have your classical BV and you kind of quantize it. But you say that you quantize it not only as a BV algebra, but there is bialgebra structure somehow.
Yeah, so I'm claiming that the BV differential acting on traces defines the bialgebra structure on traces, on cyclic words.
So this quantization kind of quantum group or something.
I'm not sure. I'd like to know better. I've seen this bialgebra structure before in the math paper. This deformed differential I have not seen.
Deformed differential I haven't seen as well, but as for so without DG, you know, that story about quantum groups, it's about It's about Lie algebras without dg, without differential, and their quantization, which gives you quantum groups. Yeah, that's the Drinfeld story like many years, 40 years ago. Yeah, but of course, this dg, it's something interesting. Yeah, maybe. Yeah, all right. So it's
So this extra differential comes from when the BV differential hits two consecutive symbols. Then you get a factor of n from contracting indices, and you get back another trace. This is the only place where the truth coupling appears.
Okay, go ahead. Yeah, it's interesting. Yeah.
So now let's do the classical limit, because that's what I said I was supposed to do. Remember, I was supposed to take the Hooft expansion, look at it as a quantum master equation of some sort. I mean, this you could call this a BV infinity structure, or just a BV structure. This is a BV structure. It's still a second order differential operator that squares to zero. And I'm going to take the classical limit now, which means I'm going to treat h bar squared the t as a conjugate momentum. Let me call it pi. So I just write the same expression, but now I have pi instead of derivative. So now I have a phase space. I have a phase space with the odd Hamiltonian. So it's a derived phase space. The derived phase space structure on essentially, it's a double of the cyclic homology. So tau lives in the cyclic homology. Pi is a conjugate variable in the dual of the cyclic homology. And so the question is, so this is the structure I would have to find in some dual dg-TFT. So my goal now is to try to understand, I have this matrix model, or better, I have a quiver with potential. I have a Concierge-Solomon algebra, 3D Calabi-Yau algebra, AS, cyclic homology, and I defined this bialgebra structure, which then became a derived phase space. I want to understand what it means. These quiver with potentials often have to do with 3D Calabi-Yau cones. What's this phase space from the point of view of the Calabi-Yau cone? That's the question I would like to address in the next few slides.
Yeah, so that's indeed. You see this as what you call the phase space, which of course you can think in at a sort of a cotangent bundle because you have whatever to do all things. But it's certainly, you see it resembles this Drinfeld story when you have Lie algebra, which is bialgebra, you add the dual one, and then you quantize it. I mean, he quantized it without dg structure, without BV structure, in a very naive way, but already non-trivial mathematically. And what one gets, it's sort of this quantization of the Drinfeld double of Lie algebra. And you do somehow something similar for dg. So it's kind of, no, I do not understand it. Yeah.
And you get this family because there is this h bar m.
Yeah, and yes. Yeah, actually, there also there might be a parameter. Very interesting. Yeah, very interesting, but mysterious. Okay.
Okay.
You still have one more slide.
Yeah, that's right. I mean, I have a few more slides, but I was hoping to use them for the next lecture too.
All right.
No, that's great. I can go for 2 more slides because then I'm out of slides.
Well, it's up to you. You can stop and then recall because still there is enough of mysterious things.
Yes. No, I mean, I wouldn't mind speaking for another slide or two if you have time, if you have the energy.
Yeah. Okay. Yeah. Go ahead.
So I would like to show how to recover similar structures from a Calabi-Yau cone. So let's be concrete. Let's take C3 minus the origin. You can consider the B model on C3 minus the origin. This is concretely there's a worksheet theory, which is the AKZS sigma model on the shifted cotangent bundle. When you do string theory, you get essentially the circle equivalent local operators in this sigma model, which are polyvector fields, divergence-free polyvector fields in C3 minus the origin. Extra parentheses here, sorry. Or you can dualize polyvector fields to forms using the Calabi-Yau form, and then you get del closed forms in C3 minus the origin. Now, if I was just saying C3, not C3 minus the origin, it would be you could describe this in terms of as the cyclic homology of the Ginzburg algebra or something like that. I mean, it's very easy to describe in homological algebra the polyvector fields in C3. But here I want to do C3 minus the origin. C3 minus the origin means that there are sort of extra contributions that are zero true forms, just because there is sort of the Beltrami-Martinelli kernel, right? There is the zero true form whose del bar is the delta function of the origin. And so if you remove the origin, it's a perfectly fine del bar closed form. Now, I'm going to observe that there is a symplectic pairing in the game, because I can take two del closed forms, take the primitive of one of them, multiply it with the other, and integrate on S5. This essentially pairs a P0 form with a 4 minus P comma true form, for example. So this means that these polyvector fields form a symplectic space. Just to see an example, I know you can take the Calabi-Yau form and contract it with the del of the Beltrami-Martinelli kernel, and you get one.
Yeah, can I think about these polyvector fields as sort of a parameters in the moduli space of deformations of the whatever derived category of coherent sheets on C cube minus 0?
So I've not done the category yet. That will do in the next lecture when I do fundamental modifications. For now, you can certainly say that PV divergence-free polyvector fields are controlled, and you can certainly say that they control the deformations of the category of coherent sheaves on C3 minus the origin. Absolutely.
Yeah, okay.
And I'm just observing that this is a symplectic object.
But symplectic, should it be equivalent to the fact that it's Calabi-Yau category, or?
No, it's a bit.
It's more.
See, it pairs up. See, there are two types of polyvector fields. Right? There are polynomials that are regular at the origin, and then there are the forms which are really exist because we remove the origin, and these are paired up. So polyvector fields on C3 minus the origin is the cotangent bundle of polyvector fields in C3.
Yeah, I can imagine that there is sort of a period. Well, I should think about it, but yeah. Probably there should be an additional parameter in the moduli space of deformations. Yeah.
You're asking about NH bar, yes. I would like to understand
that. Yeah. Okay. Go ahead. Anyway. Yeah. Very interesting.
Absolutely. So now the polyvector fields are a shifted dg-algebra, the dg algebra. So because they're the cotangent bundle of something, I kind of get a bialgebra structure. I mean, the classical limit, I should say, of a bialgebra structure on just polyvector fields on C3. So essentially, I want to identify polyvector fields in C3 with tau, the cyclic homology of your category, and I want to identify the cotangent direction with pi. So here I had this beautiful odd vector field made out of pi and tau, or a family of them, and I'd like to find the corresponding thing in here. And I mean, it's not difficult, right, to find a candidate, because polyvector fields, again, they have a bracket, but this bracket comes from an action. The polyvector fields are the fields of BCOV theory, and BCOV theory is an action. There is a cubic action which gives the bracket. So I would like to say that these cubic action, polyvector fields with this cubic action are somehow quasi-isomorphic with the cyclic homology complex with this cube. Now I've not proven it or tried to prove it. But it's certainly true if you only look at the bracket, right? If you only look at the bracket, we know that by Kontsevich theorem, pretty much Kontsevich formality, that the cyclic homology is polyvector fields exactly on the nose. Now we want to remove the origin. And more specifically, if you look at a quiver with one node and this action XYZ.
Yeah, you see, you gathered a lot of interesting questions to the very end when people are kind of tired. So maybe you kind of, yeah.
No, I was thinking of stopping here, yeah.
Yeah, maybe you'll start recalling.
We're starting a few slides ago in the next lecture.
Yeah, okay, great. Well, thank you very much. Are there any questions? If not, so
I can ask, okay, so, yeah, it's just about the Calabi-Yau algebras or categories that you get. Are they compact, not compact, both?
So in the matrix models, you start with the compact algebra with category which defines the action, define the matrix model. I'm gonna find something which deforms the smooth causal dual of that category roughly. So pretty much because you remove the origin, so you don't have the place where this original category lived before. So yeah, so typically the outcome of the Hooft expansion will be the smooth category. Like it's gonna be a deformation of it's like a deformed double of the Ginzburg algebra for the matrix model.
Okay, so you expect smooth but not proper or compact.
Right. Yeah, unfortunately, it will never be smooth and compact. It's always a bit of a non-compactness in the game.
Okay, thank you.
And making sense of the cobordism hypothesis in that context is part of the genus expansion.
Formally, yes, it requires compactness, but still, so we will see. We'll see. Okay, so thank you. And the second lecture will be the same time on Wednesday. Yeah.
Okay. Very good.
Okay. Thank you.
Thank you.